specialty contracting business in 1973 and has worked in construction since. In 1996, Roy became involved in regional engineer for Eurotech and concrete stabilization technology, and has enjoyed working and helping in innovative advancements with engineering across the region. We'd like to welcome Roy. To get the credits for engineering credits, please sign up here. If you're out of state, we have some forms up here that we can fill out when you're done. If you need those, if you're out of state people. There you go, Roy.
We'll go.
Go for it.
The talk, like he said, is on frost heave mitigating using polymer, and a lot of you people are familiar with that. We'll take some photos, look at some photos. But and the exciting part about this project is working with Tom Edgar at the University of Wyoming is we can do the frost heave prediction based on our injections that we have. So the way this started is Tim McGarry came to me and he had a problem on, we'll go through the projects, but we had a problem, and so he brought me out, we reviewed the site, got University of Wyoming involved. We took a look at the effects that was going on I-70, and then went through with the project. We'll be going over the test results, including the frost heave in the next 2 years after we did the construction, and then we'll have some conclusions at the end of this. This project is in southern Wyoming. It's on Wyoming 70 on the way back from Medicine Bow National Forest. This Highway 70 is closed in the winter, and there's about a mile past where this frost heave bump was. There's a parking spot, which is a popular place for snowmobilers to depart. So they would come up there, snowmobile all day, and on the way back, they would hit this frost heave. This is downhill from left to right, and we'll take a look at some of the geology. Right here, on that bottom line, there's a rock outcrop that comes across from the northwest to southeast direction with water behind that as we're coming down that hill, and that's one of the requirements for having the frost heave. Tim McGarry was familiar with the Eurotech, as we've done a lot of slab leveling, bridge approaches, taking care of soft soils at depth. In his district, he's the maintenance engineer, District 1, and so he's the one that came up with that idea. He says, Roy, can you go ahead and put some material under there to give me some insulation? We looked at the site and says, let's give it a try. So we were planning to inject a thin thermal barrier in there. We know that the material can withstand the beating of traffic and actually improves the subgrade condition of that soil that's below the asphalt. And it's impermeable to water, so as we inject that, we're going to have any lensing that goes down into that soil, we're going to be stopping that water flow, that water migration, which is required for frost heave. So we brought in, Tim McGarry and I, we brought in University of Wyoming. Tim actually had this financed using a research project from WYDOT headquarters, and so the plan was to verify movement and lift before and after the project, and they ended up also proposing to put thermistors into the ground to measure the temperatures over the winter periods, and they also check for water elevations on a continual basis through this project. Like I said, Tim McGarry was interested in this because he knows the characteristics. We'll be taking a look at that, but he wanted to provide minimal disturbance to the project. This material, this process has been used with YDOT before and with UDOT. I think the first project was up in Region 1. The first project that we actually went below asphalt was on Highway 84 coming out of Weaver Canyon, and Kent Nichols was involved with that, where we had some sinkholes developing in that highway when they were they were resurfacing that. So as they came across with that vibrations, little sinkholes developed, and here's Kent right now to help out with the presentation. And we'll be taking a look at how this material works. But we had some rotted material that had been going on since a flood deposited material in 1950s, and those voids placed, that rotting of that refuse is what caused those sinkholes. So the first project like this in the United States was completed here in Utah up on the mouth of River Canyon. So that's talking about some of that stuff we learned at lunch. It's that teamwork and that innovative part that UDOT has that's willing to look at these things. So the goal was to provide an insulation barrier in the plans. We'll take a look at this. Here would be the research plans that was presented to the research board, where we would put in the insulating layer of polymer, transistors before and after to measure temperatures continually, and then also they were taking a look at that water control. So when these transistors, or these thermistors, I mean, were put into the ground, the same material was put back in and tamped so that we did not alter the characteristics of the soil and the temperature gradient in those zones. So right here is how that works, what's going on underneath that project. If you guys can see this, he put this in, it was started right here. This particular material expands 15 to 1. The material we used on this project was 20 to 1. It's Urtec 46 star, 3-pound free rise density. So you can see how that's coming up, and it's exothermal, so there's actually heat in that glass right now. You could feel it, and it's warm. It's also tacky, and we're just about ready. You can see there's a little bit of tackiness in there, but as this stuff goes in through that soil, we're developing a layer, and we're getting some lensing. So that 3-inch layer may be actually over 4 or 5 inches with some lensing coming in. So this was the proposed research plans. We ended up getting data right away, getting the elevations. So the actual frost heave site is shown here. And here in the bottom picture is where that big bump was that was causing the problems with the snowmobilers coming back out of that canyon. The heave in this location ranged from 4 to 6 inches. It would raise in the winter and then subside in the spring. February was probably the maximum. February or early March was the maximum elevation change during that frost heave process. So, and they found that consistent right towards the end of February, 1st of March, for the 2 years they took the continuous monitoring. This is the site again. We've taken a look at this, but as we take a look at that top right picture, that's a rock ridge that's coming down. It happens to cross at the location where the frost heave was occurring, that rock ridge. And when this was constructed, it was proposed to cut into that crystalline rock 3 feet. The contractor had a hard time, and WYDOT agreed to allow the contractor to put down 3 feet of fill over the ridge, and then taper the ends of that on the approach side and the departure side. So what we have is 3 foot of fill here now. We have that rock formation in the same place, and we have a way to hold that water. That's initial error, I guess, that as we're looking in designs we can pay attention to, and guys in maintenance get to have the headaches for that later. But as we understand it, we're all going to get better, like the talks have given, one day at a time. The material, we'll go right to the bottom. The material, the fill material they took out was SM-A24 and A40. And as we take a look at this chart, there's 3 things needed for frost heave. The cold temperatures, and we get that annually. The source of the water, and we saw where that was developed as we had water table in there that was not allowed to escape. And then we have frost-susceptible soils. This sandy silt or silty sand is just about the very worst. The reason is we can have capillary action, so we can draw that water up to that freeze zone. And as that water's drawn up and that freeze zone's going down, we get those crystals. It's not that that hard water that freezes, but it's crystals that's building on that soil, inside that soil, to expand those sand and silt particles with the water crystals hitting that right at 30 degrees. As it bounces back and forth, those crystals build. And then as we move that frost heave down, it's building at that next level and pushing everything up. So that's the conditions we have here. When we later in the presentation, we're going to be taking a look at the characteristics, the thermal characteristics, and what we did was this average between the fine sands and the clays in order to get characteristics. But remember where we are on this chart. So here's the elevations over on the right of what we had. The top red line is the center line of the roadway, and that's got a high lift, 6 inches plus, and one time we heard it was up to 11 inches, but I don't know if that was never measured. But we had 6 inches plus of lift over the years. The second is the center line of the eastbound, the downhill side, where we have a dip in that frost heave. And that dip occurs right over where there was remedial action remedial attempt put in the 1990s to mitigate that frost heave. So this pipe, this French drain came in, and it's in that lower one. It came from the center line, and then was to take that water out to the downhill or the eastbound shoulder. That worked, but however, when they put that backfill in, they ended up using a material that didn't have the capillary action. It was a larger aggregate material, so we did not have that frost heave in there. That gave us that extra dip, which allowed us to have more frustrated public driving down that road, picking up speed and getting home after a good day of snowmobiling. I'm going to go back just to recognize, here's where that dip is. As we come back to this slide, in that center lane of the eastbound, which is the blue line, that's where that dip occurred, right at that French drain that was backfilled with different material. Is that understandable? Good. This is an injection gun that's used to put the polymer in there so you guys get a little bit of a feel. There's an A component and B component that, that Ken had mixed up and stirred up. The reaction starts right away. You can pass that around and you can feel the lightness of it, and it sets up very quickly. So there's a lot of control in the application, and the technicians make a difference. The very good ones are very good, and the pretty good ones are pretty good. But anyway, it's a two-part, injected at the nozzle. It's an instant mix, and then it goes through that gun and down through a tube to the desired location. So what we had here is we're injecting at about 18 inches, it's 18 to 20 inches, and in order to get that zone, we want it to be underneath the road base into the subgrade, into that silty sand material. Here we are, taking a look at it. Here's where the difference comes from the good guys and the very good guys. You can see right here there's a dip in that road. It's pretty difficult. We have to check our spacing of our guns in order to get a uniform coverage under there to give us a uniform lift, and in this case a uniform insulation layer. So they had to work hard. They timed their injections. They do have it set up, so we had to do a little bit of bouncing around during the construction to keep that rideability and make sure that we had that material in uniform. The surface rise is the way we detected and knew that we had that 3-inch. We set up target elevations at the surface of the asphalt, and had a little bit of irregularities. There was irregularities before we started, and then after we finished the project, when we were injecting for 3 days on this, and then the 4th day, we came in and milled it to get that surface back. After it was remilled, elevations were taken, and that became the benchmark for the next year's data. Here we are, the surface rise in the transverse direction. As we are on the left side of this bottom chart, that is the shoulder of the eastbound lane. We're going to the center of the eastbound lane, to the center lane, and then we had the transition zone on this as we moved over to the westbound lane shoulder. So there was no problems. Again, that problem was because of the extreme problem was because of that attempt to mitigate the frost heave with that French drain. On that top chart, the zone for the full 3-inch treatment is in that darkest gray pink, and then the lighter shade is the transition zones coming up to it on the eastbound side. And we went across it, transitioned down on the east side of it, and then also transitioned in the westbound lane. The elevations were taken at 10-foot centers, and this is during the season, through the seasons. It's taken every month on a monthly basis. So we had those readings those are sitting down on this, on the bottom. We have the solid lines are the 2011, and the dashed lines are the 2011-12. The dashed lines are the 2012-13 elevations. The top solid line is the elevation that was taken in January prior to construction. So you can see how that frost heave has dropped in that treated zone. That bottom solid line is the thickness, charted thickness of the injection of the polymer material. So
how do you know how deep to go to start your project?
we wanted to get below the base, the asphalt material, the base material, into that fill material and stay as close to the bottom of the base as possible.
Bottom of the untreated base?
Yeah, so we went a few inches below the bottom of that base, knowing that there'd be some silt above it that would give us a small frost heave, possibly, or maybe we wouldn't have any frost heave there because we wouldn't have the permeation of the water to that zone. So we kept it as high as possible. It made it very difficult to keep that asphalt smooth. The work was done in October, I think around the 20th. And the reason for that is we wanted to have that asphalt pavement as stiff as possible, so we had less turtle humps, less bumps and rocking and rolling, less waves.
Is there a depth limitation, how deep you go for DP? Is there a limitation to what your product will do?
We've injected to 30 feet across the country. They've injected to 60 feet, but
And it'll actually feed the material or section up?
on this right here, we want to keep, the frost depth is probably around 4 feet. So there's no reason to go any place below probably two feet, depending on what kind of soils we have. So yeah, the timing of the material makes a difference on how deep you can actually inject. But for this frost heave mitigation, it was only shallow injections that was desired and required. Again, that was January 26th, that top elevation, January 26th of 2011, prior to the October construction. This is the heave in the center line of the highway. We see we don't have that extra bump in there. It's more of a transition, but it's still a radical heave, and it was causing problems, so they had to mitigate it somewhere. Unfortunately, the mitigation ended up giving the second little vault and probably decreased the safety on that portion. We were a little more uniform on the coverage of and the lift during the injection of the material in that center line than we were in the center of the eastbound lane. After the injections, this is the transverse frost heave as we're coming from the shoulder of the eastbound lane across the center line to the shoulder of the westbound lane. The only data we have prior to the injections is right here on these transverse lines. We have 2 points, and you can see there's a substantial decrease on those 2 data points. One of the things that's interesting on this, and we found quite revealing, the area on the westbound lane that didn't cause the problem has the most heave after we finished, which makes sense because that was on a transition. So we transitioned from that center line to that west line. So now, as the shoulder of the eastbound lane towards me on this graph, has very little movement. As we run across that transition zone in the westbound lane, the frost heave looks like it's become problematic. So it verifies, I guess, that we were able to get that insulation down and help prevent that frost heave. This is a closer up of that frost heave coming from the south side of the highway to the north, or from the shoulder of the eastbound lane over to the right. And on the top is the only 2 data points in that thin line on the pre-construction. Now we come to the fun part, the part where we get into temperature readings, and where I'm kind of blown away with some of the minds that worked on this to be able to predict the heave, or the frost heave, or the freeze depth, to predict the freeze depth. And then from there, depending on what kind of soils we have, we'll have a variance of the frost heave. Again, it's dependent on the soil types. Right here we have number 4. It's just circled up with the thermistors injected. Here's hole number 3 in the transition zone, and hole number 1 that had no treatment or no injections on that hole number 1. So we'll be reviewing that. We'll be reviewing the hole 2, 4, and 6 on that eastbound lane. 2 is to the left and 6 is to the right of that unit, hole number 4 right there. So this is the 2-year temperatures in hole number 4. We'll see that we got close to 0 degrees centigrade, and stayed there fairly consistently. We have the hourly temperatures that's plotted to get us down to that area. That they use the hourly temperatures over the period of time, and as we had continued recording on those thermistors. So that thin gold line at the bottom, that's the top, that's above the material. Let's take a look at that. And that goes down below 0 and stays pretty consistently at below 0. And we'll be comparing that to hole number 1, where we still have a consistent drop, but hole number 1's on the right, hole number 4's in the treated areas on the left. These charts are built for everything on the full report, but you'll see we're coming down to that 0 line, and on the number 4, on the 560, or the thermistor that's right below the material, and the deeper thermistors recorded above 0 and never did get down to freezing. So on hole number 1, everything came down all the way down to that 560 and that 800 millimeter depths. I have to study just a little bit that chart. The 1200 meter depth was it was lost and couldn't get recovered halfway through the project. Here's the temperatures at hole number 4. There's a correlation here between the subsurface temperature at the 560 millimeter depth and the elevation differential on the top chart. So as we see where that 560, or the zone right below the injected polymer, hit that freezing zone, it was able to still get enough water and get the water to cause the slight heave above there. So again, it's that crystalline layer. It was down there long enough that it built the layers, run down. We don't know how far. Tom could probably figure it out and calculate about how deep that frost did go during that cycle. The prediction of the frost heave can be determined. There's several models been proposed to determine frost penetration, and in the literature, the most commonly used is the modified Berggruen equation. It's developed by Aldrich and Pettner. 1953 is how long this has been going on. They were researching frost heave in Arctic, and Minnesota DOT came up with a simplified version, which we'll take a look at. This is what's used to be able to determine frost depth from characteristics of the materials that frost is going through, and the daily temperatures as they're recorded. So daily temperatures below 0 or below freezing, 32 degrees or 0. So with the modified Berggruen equation, let me get back. It was, again, Tom Edgar said that the modified simpler equation was satisfactory and the assumptions worked well. This is a modified Berggruen equation where we have the air freezing index. It's the number of the degree days below 0 degrees centigrade and that's measured 4 foot above the ground level for whatever reason, I don't know. But this will give us a representation of the amount of thermal energy that's available for freezing materials below that. In this formula, Z is the frost depth. Then we have the K is conductivity, thermal conductivity for the material. The air freezing index, again, ratio is N for modifying that for the general freezing. And then finally, in here, Lambda has it's a modifier. We threw out the modifiers and used the simplified version. That modifier is usually, going back here, the N is usually someplace, it's usually sitting around 0.9, and L is usually sitting around between 0.7 and 1. So they can cancel out each other out close enough that we could start working at that soil. So we use this modified equation, and what we have is the freeze index is or the Fi. It represents the amount of energy required to freeze the layer, depending on what thickness that is, the layer, which can be determined by the equation so the thickness matters. As we're taking a look at the actual characteristics, we have from the Minnesota Department of Transportation, we use their numbers for the freeze index requirements for asphalt and for the soil, which varies depending on moisture content or the road-based material. And then for the silty sand material that was put in by the contractor, we just took an average of the fine sands and the clays to get to that silt calculation, and just average those two in doing the calculations. From this equation, we can determine the depth that frost is going to go based on the thermometer or the temperature index records over the years on a daily basis or hourly basis, as we find out how far that frost is driven down. Here we have the formula, and we won't run into that, but the conductivity of the frozen ground was determined by the average of the freezing sand, which I mentioned. Portland cement, asphalt, those things are all calculated and are available for the calculations as we determine what we need to do for that injection layer. We have to have the freezing index required, again, that can be determined based on the thermal characteristics of each layer, so we can find out how far that frost will drive down, or conversely, what type of insulation we're going to be needing. We have, during the days, we have a total of freezing index based on the temperatures of 1,206 Fahrenheit days in year one, and in year two, 1,355. So with this average daily temperature, finding the freeze index, we can go ahead and plug that into our system, plug that into our formulas, and this is the charts of that freezing index in year one. From that, coming back on here, this here is plugged in to those formulas earlier. You want to go back, anybody? No. We'll take a look at it. It's nicer when you can go back and forth and kind of figure this out. But anyway, based on that freezing index, temperatures taken at the site with some thermistors, and also taking a look at previous years with at Encampment, Wyoming, and the Highway Department has some other surface temperature gauges in their asphalt that they use for determining snow plow and salting and that type of stuff. So the volumetric latent heat diffusion for the granular materials is based on this. It's in BTUs per cubic foot. That is important because it's going to take so much heat mass or so much freezing index volume to get this frozen, so we can migrate the frost down through that soil. There's no equivalent to the value of the latent heat of the polymer material. Tom Edgar came up with this behind my back. He didn't tell me. But this is the number that's used, which is about equivalent to 18 inches of the soil. So When we take a look at that, we've got the before and after calculations to be able to predict that frost depth. They're plugged in, and we're going to just go right to a chart so we can kind of look at the summary. This here is the numbers plugged in. Again, the BTU preferred was calculated by Tom Edgar of the University of Wyoming using reverse calculations for that zone and comparing that non-treated hole number 1 with treated hole number 4. Summary. I guess this is the part where it gets a little exciting, if you get excited with this, is those predictions are recognized as we have the measured depth of the soils using the thermistors and the calculated depths. And the biggest variance is hole number 3. If you remember, that's on the westbound lane. In the center, it's in that transition zone, and I think we had probably the most variance, or the highest percentage variance of getting our material in there. So, so that's the results that we can end up detecting and calculating and finding that and predicting the frost heave depending on what we have. As we're in that new construction, the typical ways is exclusion going around it, rebuilding it, or using rigid polyethylene, I think, material to prevent that frost heave. Tim and Gary had done that and had some problems. He did it on a retrofit, put that in, and had some problems. He just moved that sharp edge down. So that transition, that's one of the reasons we put in that transition zone. And in new construction, I guess that transition zone is important to have that if you're building new projects and you have some kind of silty material that's going to give you potential frost heave. Summary, it appears to work well, preventing heave by altering the thermal regime, providing for the structural support and controlling some of the water movement is one of the possibilities of why we ended up having that. The operations in this case was able to do it one lane at a time, keep that traffic moving and during hunting season, and if you stop those hunters for too long, they could be upset, and they're armed. The operation occurs in one lane at a time, and in this case we used 25 millimeters of polymer is equivalently to 150 millimeters, or 1 inch of polymers equivalent to approximately 6 inches of soil. And again, we had on this zone here, we brought our freeze zone up about 18 inches. So Tim and Gary came up with the idea. It's interesting to see the different states that come up with ingenious ideas, and it's important, I think. Tom Edgar, again, was the muscle behind this project. Chris Potter was a graduate student and gathered the data and did some initial reports on his master's thesis. The Y-Dot crews were awesome to work with during the recording and keeping everything clean and making sure that data could be collected. And then other people I'm appreciative of the crews at Concrete Stabilization Technologies, as these guys are the ones that actually made this thing work by getting a uniform enough material in place. So anyway, some of this stuff is interesting to start, and some of those formulas get a little bit scratchy. Questions? Questions on the applications process or anything else that can be discussed using the polymers. Did that glass get all the way around? And get, oh, here it is out in front. I'm going to take that. I just want to, I'm going to see, but let me get somebody to, let me just find some. You're big, Steve. Go ahead and just kind of break that off. It's not that much. It's pretty used, but just kind of break it in pieces. We can get it out of the glass, but that's hard. Just feel that. Yeah, it's
Pretty tough.
one of the nice things about this material that we're finding. It's worked for a lot of different things. Underneath this project we just completed, when you feel that tensile strength in there, and the tensile strength's just about equal to the this is an advertisement commercial. The tensile strength's just about equal to the compressive strength. So as we're building, as we're repairing the ground, like I told Tom Edgar, I says, we just fixed the dirt. But if we're repairing that ground or putting insulation in there, this material is going to help hold things together, and it's going to improve the subgrade in a lot more ways than one. I don't know, is Kelly Shield here? Okay. Kelly Shield's out at the Concrete Stabilization Technologies booth. But Kent and Kelly are available for answering questions like that. If we do have a frost heave project, they can get a hold of me and I'll become involved with you guys to partner up and find a solution. Anyway, and we've done the commercial, done the presentation, went through the tough stuff.
So how do you know when to stop?
We-
When it gets level, or?
We're, on this thing here, we're monitoring. We set up target elevations for that hole in a grid. So we had to set up, we wanted to lift that to that 3-inch zone to make sure we had the 3 inches of material in place. So, and there's going to be some variance in that. There was variance when we started, and that's why we had to do a grid when we were running those elevations and doing that injection to lift it. But it's not going to be completely consistent. Yes? We started, I think we started on a 6-foot grid, and then we came back in, and sometimes we came back in on a half grid, and sometimes come back in on a 5-die grid, depending on how we were moving along and how stiff that material was and how uniform it was lifting. So and then we did some fine tune-ups where, you know, let's go ahead and drill another hole here. So there was some tune-ups, and that's the reason it took 3 days. We just wanted to make sure we got it right. We didn't want that's good enough to be good enough. We got a question from the maintenance guy in the back. Can I leave now? Anything else? John, you got some. What's your thoughts on that? Yeah. It was a fun research project, and it's fun to work with Tom Edgar. And so you guys get to work with the guys down at, like Kyle, you get to work with those kind of guys. It makes it a lot of extra fun and extra work and extra lamps at night. So I don't have more. What do we get penalized if we don't?
Penalized, no. Thanks, Roy.
You guys can have a continuing credit. It'll just this much short.